Welcome. This is the third part of AMC10 Week 3 solution video. Problem 15. So in this problem, we assume that E, B, F are collinear. So therefore, let me connect these 3 points. So the angle here is 60 degrees. The angle here is 30 because this angle is 60 degrees. So as a result, here we have a right angle. So the triangle AEF is a right triangle. Moreover, this is a special right triangle because the angle here is of 60 degrees. Because of this, we know that AF over AE is equal to square root 3, which is the same ratio of BC to AB. So the correct answer is C. So first, let's observe that the difference between 4/5 and 3/4 would be equal to 1/20. 1/20. So suppose that AB is somewhere between 3/4 and 4/5. This is 0.75. This is 0.8. So then we know that as long as B is less than or equal to 20, there's a unique one for each B. There's a unique A such that it is between 3/4 to 4/5. Because otherwise their difference should be bigger than 1/20. So let's first try if B equals 6 is at all possible. Then we run B equals 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, everything before 20. So it's not possible for B to be 6 because otherwise we would have that A should be somewhere close to, A is somehow 4.5. A has to be bigger than, so A is equal to 4, that's too small. A is 5, that's too big. So that's not possible. That's not possible. When B is equal to 7, we need something close to 5.25. A is somewhere 5.25. So the next choice would be either it's 5, it's too small, then you have to choose 6, but the 6 doesn't work. When B is 8, then it should be, A should be 7, because it should be strictly bigger than 3/4. So that's not possible. Also, this is 5 points. And for 9, there's an easy way to find a fraction that's somewhere in between, because 3/4 and 4/5. Let's add 7. 3 plus 4 is 7. 4 plus 5 is 9. So that is a fraction that is strictly between 3/4 and 4/5. So this is the quickest way to find one rational number that is between two rational numbers. So that's good. 7 over 9. That's good. That seems to be the first one that minimizes A plus B. But what we need is to find the fifth number. So at least we need to find another 4. So how about 10? For 10, it needs to be somewhere A is bigger than 7.5. So A should be equal to 8, but 8 over 10 doesn't count because it's not coprime. 8 and 10 are not coprime. So let's try 11. For 11, A is bigger than 8. It's 8.25. So let's try to choose 9 over 11. So 9 over 11 is not good, I would believe. 9 over 11 is slightly bigger than 4/5. So that doesn't count. How about 12? For 12, well, it's 12. So then A is equal to 9, but this is not a 9 and the 12 are not co-prime, so that's not a answer. For 13, then A is 9.75. So if we choose A equals 10, that probably would work. Yes, so we have another fraction. 10 over 13. That's the next one. That's the first one. That's the second one. And let's try 14. 14. So A is almost equal to 10.5. So let's see if A should be bigger than 10.5. So let's try 11 over 14. So 11 over 14 should work. That's a number somewhere between 3/4 and 4/5. For 15, we get A is equal to 11.25. But then you try 12 over 15. That's not co-prime. That's not in the simplest form. So 15 doesn't count. So 16. 16 is not good because A would be equal to 12, but you cannot choose 12. A has to be 13, but 13 is over, so that's not. So let's go to 17. For 17, A should be strictly bigger than 12.75. Let's try 13 over 17 to see if this. Yes, so that's a good number. So altogether we have found 4. So let's try the last two. For 18, A should be 13.5. So we choose A equals 14. That won't work because 14 over 18 is not in its simplest form. And if you go two steps, like 15 over 18, of course it's not in its simplest form, and you go further, then it's too much. So let's see 19. 19A is equal to or bigger than 14.25, so we can try 15 over 19. 15 over 19, that would be equal to, yes, so that's a good one, between 3/4 and 4/5. So 1, 2, 3, 4, 5. That's the number fifths, and the A plus B is equal to 34. So the correct answer is 34. It seems that there's no theory to do so. You just have to try one by one. That's my method. Problem 17. So for this problem, the easiest way to do the job is to notice that if we draw two lines here, then we have a right angle here. And since we have a right angle here, right angle here, then these 4 points must be on the same circle. And as a result, this angle is equal to that angle, which is equal to 45 degrees. And now what we need to do is we can just move the triangle ABC to here. We just draw another triangle of the same shape, C prime. And you can draw a line from O to C prime. So because of the symmetry, we know that OC is equal to OC prime. It's because of the symmetry. And at the same time, because of the symmetry, we know that this is 45 degrees as well. So we actually, this triangle OCC prime is the so-called isosceles right triangle. As a result, we know that since OC is 8 square 2, then we know that CC prime is square root 2 times CO, which is equal to square root 2 times 8 square root 2, which is 16. And since BC is 10, so BC prime is 16 minus 10, which is equal to 6. So the length of BC is the same thing as AC, so the correct answer is C. Problem 18. For this problem, we will see that A and B are not allowed. And for C, we will create a scheme to do so. Suppose A is the answer, then we would see that starting from the first climb should be 16. And the next one must go by 9. And then the position of the monkey would be 16 minus 9, which is he is at the 7. And then we have the problem because it cannot climb up because it climbed up by 16. 16 plus 7 would be 23. That's not allowed. That's not allowed. Okay. It cannot going down because going down must be -9, which will be out of the range. So 22 won't work. So A is not the answer. For 23, actually, it is possible for the monkey to climb to the top. The problem is that for 23, it's impossible for the monkey to climb down. Let's prove that. So for 23, we have the following problem. So starting with 23, the only way for the monkey to go is to go down by 9 and 9 twice, which is 18, so that you get 5. And then you climb up by 16, then you will get 21. Then climbing down by 2 steps, you get 3. Climbing up, you get 19. Climbing down by 18, you get 1. And climbing up, you get 17. And at this moment, you can only climb down by 9 once, and you get 8. 8 is a forbidden number because at 8, you cannot climb down or climb up. You climb up, you get 24. Otherwise, you get -1. So both, in each way, it will be out of the range. So that's a not allowable one. So A and B are not the answer. Will C be the answer? Yes, we can create a scheme to do so. So starting with climbing up 16, then go -9. So the monkey would be at the position 7. Going up 16, you get 23. Going down by 18, it's 5. 16 again, 21. Going down by 18, you get 3. So if you're going up 1 step and going down twice, you actually reduce going down by 2. 16 again, 19 minus 18, you get 1. Starting from 1, you get going up 16, it's 17. Minus 9, you get 8. So 8 is actually a good number here because you're climbing up 16, you get 24. That's the top of the pole. And let's see how to start from 24 to going down. So minus 18, you get 6. Going up 16 is get 22. Minus 18, you get 4. Going up 16, you get 20. And the minus 18, you get 2. Going up 16, you get 18. For 18, you're going down 2 steps, you get 0. So from all these 5 answers, 24 is the smallest one that works. Problem 19. So this is a difficult problem which combines algebra, solid geometry, and probability. So let's first find out the criterion for the quadratic equation to have at least, to have exactly one root between -1 and a +1. So by the assumption, we know that there are 2 ways that there will be one root that is between -1 to +1. So the first case is that so y equals ax squared plus bx plus c represent a parabola. So there would be a case that the parabola is tangent to the x-axis so that it has exactly one root. And if that root turns out to be between -1 and a +1, that should count. But that's of 0 probability because it's very special for the quadratic equation to have double zeros. So that's the first case. The second case would be if the quadratic equation, so let me just write it, fx equals ax squared plus bx plus c. So f1 is equal to a plus b plus c, and by our assumption, it is always positive. So if there's exactly 1 0 between -1 and a +1, so f -1, which is a minus b plus c, has to be negative. So the criterion for the quadratic equation to have exactly one root between -1 and the +1 would be a minus b plus c less than equal to 0, less than 0. So that solves the algebraic part, the criterion for ABC to have for the quadratic equation to have a negative, to have one root, one and only one root between -1 and the +1. The next one is the solid geometry part. So A, B, C are sitting between 1, A, B, C, and 3. And this inequality can be represented by the plane and all the points below that plane. So the question is, what is the volume of this plane cutting through this cube? So let me draw the picture. So suppose I have a cube like this. So in order to see that a plane cut this cube, so the cube has altogether 12 edges. So let's find out all the edges that the intersection of edges with respect to the plane A minus B plus C. So the edges can be represented by the following 12 points. There are 12 edges, so which we can write them as 1, 1 arbitrary C, 3, 3 C, 1, 3 C, 3, 1 C, and 1 B 1, 3 B 3, 1 B 3, 3 B 1, and also A 1 1, A 3 3, A 1 3, A 3 1. And let's see which one are possible. So this one means A and B to be 1, but since C is at least 1, so this won't work. And the 3 3, the same thing. A minus B is 0, 3 less than 1, that's not possible. And the 1 3 C, so A is 1, B is 3, then it's possible that because C is 2, right? And the 3 1 C, that's not possible because A minus B is already positive, C is positive, that's not possible. 1 B 1, so that's possible because 1 2 1 gives us the answer. 3 B 3, that's not possible. 3 plus 3, A plus C is already too big. No. 1 B 3, that B has to be equal to 4. No, not possible. 3 B 1, not possible. So for A 1 1, A has to be less than 1. That's not possible. A 3 3, not possible as well. A 1 3, that's not possible. The only possibility is 2 3 1. So 2 minus 3 plus 1 is equal to 0. So let's mark these 3 points on the figure in the left. So we know that A is this direction, B is that direction, and C is the third direction. So where is 1, 3, 1? So this would be this would be 1, 1, 1 point. Let me erase that. Okay, so 1, 3, 2 means for A it is 1, but for B it's 3, so it has to be somewhere here, but then you have 2 here. So that's the first point. That's 1, 3, 2. And the 1, 2, 1 means the point A is there and the C is there, so it's somewhere here. So that's 1. And the 2, 3, 1 means for A it's somewhere in between, and for C it is equal to C is in the bottom and the B is here. So we have the point here. And therefore you would get, let me draw back the picture. Therefore you would get the intersection of the plane to the cube is just to cut one corner of the cube. And what is the volume of this small tetrahedron? So this tetrahedron has a base isosceles right triangle with side length 1, 1 with height equal to 1. We know that such a tetrahedron, the area would be 1/6. Basically, the area of the triangle is 1/2, and since you have a cone over it with the height 1, so then the total volume would be 1/2 times 1/3, which is equal to 1/6. So this solves the solid geometry part. The probability part is actually quite easy because the total volume of the cube is 2 by 2 by 2. So the probability would be 1/6 over 2 by 2 by 2, which is over 1/48. So A is the correct answer. Problem 20. The answer for this problem is D, 77. Let's first see 76 doesn't work. I can create 76 numbers so that none of the two, one is 3 times of the other. 1, 2, 4, 5, 7, 8, 9, 10, 11, with number 3 and number 6 missing. So altogether there are 9 numbers. And also 34, 35, all the way through 100. Totally 67 numbers. So adding together, this 76 numbers. For these 70 numbers, it is easy to see that none of the one is 3 times of the other. So now we want to prove why 77 should work. So I will create 76 sets. And if you choose 77 numbers, at least 2 numbers has to belong to one set. And in that set, one is 3 times of the other. So what I want to do is 1, 3. For the first 9 numbers, I will just multiply them by 3. 2, 6, 4, 12, 5, 15, all the way 11, 33. So this gives me 9 sets. And for the set 34 to 100, either we may make them a single set number, for example 34, 35, or in the case if it's divisible by 3, then we divide it by 3, 12, 36, and then 37, 38, 38, 39 becomes 13, 39, And you know the pattern. The last one would be 100. There are altogether 76 sets. If you pick any 77 numbers, at least 2 of them has to belong to one set. And in that one set, one is the 3 times of the other. That concludes the proof of this problem. The answer is D.